It's like she said that we have to meet like 45% of this and like 80.
All right, good evening, everyone. Welcome to the last week of classes. Okay, how did the homework go?
17 and 18. I wasn't sure what the formula was going to be to solve those.
Okay. Okay, put them on chat. That make these things easier. Can you guys put them on chat? So 17, 18, other questions? Any other question besides 17 and 18? Anybody? Okay.
Not at this moment.
Not at this moment. All right. So
Well, no, anybody else?
yeah, okay. All right, so I'll start with 17, 19, and if you guys have any other question, I will be glad to mention them. So, okay, let's look at number 17. We are in section 4.2. This is the problem. The half-life of plutonium-239 is 24,100 years. So the half-life is the amount of time needed for the initial amount to be reduced to half its value is 24,110 years. By what percent does a sample of plutonium decrease after 1 year? So what they want us to find is the rate of decrease. By what percent? Okay, by how much? It means they want us to find the R. What is the R? So what they didn't tell us that the life of plutonium is an exponential function, but they assume that we are assuming this, and they did not give us the initial value. But still, they want us to find the rate of decrease. So how are we going to set up this problem? So we're going to say, let f of t represent the amount of plutonium after t years. Okay, and we don't know really the formula. The only thing we know that it's exponential. It means it has the form a certain initial value a times b to the power t. Okay, a is the initial value and b is the growth factor. That's all we know. And what they want to know is r. We know that this is decreasing, so we know that 1 plus r equal to b. So if I can find the growth factor, I can find my r. Can I find the growth factor? Did they give me enough information to find my growth factor?
Yes,
Okay?
because if you double the half-life, then that's your initial value, right?
If I double the half-life, that's the initial value. That makes sense to me. But how can we write? So this is decreasing. Okay, what's this is unknown to me. I know that right here, 24,000. I know that right here I have 24,110. That's what I have. It means I know that after 24,110 years, I have half what I started with. How can I use this information to find B?
Was that T?
What? That's time, of course, that's half-life. Half-life is the time needed for the amount of plutonium to decrease to half its value. That's a T, that's a time, that's what the half-life, how long it took. Let's make sure that let us use this information. How can I use it? Is that the value of the plutonium after 24,110 years will be equal half its initial value. That's how I'm using the fact that the half-life is 24. It means if T is 24,110, the output is half of A. Now, why will this be enough information? What is F after 24,000? It's A, my initial amount, which is I don't know, but most probably I don't need it, times the B to the power 24,110. This is equal 1/2 times A. Another question is, I want to find the growth factor or the decay factor in this case. If I know my factor, I know my rate. Can I solve for B? Can I solve for B?
Yes.
Yeah, because of course I need to isolate it. How do I isolate it? I divide by A both sides. So divide by A. When I divide by A, this, both sides of the equality, I will get B to the power 24,110 is actually equal to 1/2. And now what is B? Okay, we have to take, we want to get rid of this
LN,
power.
right?
What?
LN?
You don't really need ln in this problem. Okay, you don't need ln. It's like if I ask you to solve x to the power 3 equal to 4, do you need ln?
No.
No, it's the same problem because you need ln. When do we need ln? Let's get that very clear. You need ln when the unknown is an exponent.
Oh, okay.
Right? We don't, the unknown is not an exponent, it's just a number. It's a weird number, you know, but it is actually a number. So how can we get rid of this number?
To the power?
To the power 1 over that. That's what kills the number. So this is going to give me 1/2 to the power, or the 24th 110 roots, if you want, to the power that. Now, this to this power will give me the B back. And this is just a number that we can compute. It's a really weird number, but we can actually compute it. So we're going to get 1/2 or 0.5 raised to the power 1 over 24,110, close it, and I get 0.99999. And I'm not going to actually round it up because I don't want a 1. Okay.
I think the book has 0.0029 is what they have as there.
Yes, because I did not find the rate yet.
Oh.
B is, that's the growth factor. That's the B. Okay, now what's the rate? We know the relationship. 1 plus the rate is my B. It means the rate is always the growth factor minus 1. So the rate is, that's my growth factor. I'm not going to remove from the calculator. I'm going to take 1 away from it. And this is going to give me minus 0.0000287. So it's decreasing very, 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 very slowly. It makes sense because it took 24,000 years and 110 to be able to lose half of its value. And that's explain why the rate is very small. It's taken it forever to lose half its value. And it's the problem. Okay, I will put those problems I'm solving, 17, 18, I will actually put them on Blackboard for you in case you were not able to write them correctly. Okay? All right, so let's look at 18, but this one I want you, I don't know if it's verbatim the same or not. Yeah, so let's look at number 18 and let us set it up together. So number 18, it's another kind of chemical that decreases. And here they tell me that the half-life of carbon-14 is 5,730. And the question is, by what percent decrease after 1 year? So they want basically the percent of decrease. And of course, it's going to be very, very small because the half-life is very large. It means it's decreasing very, very slowly. And so the picture, just to help you out, so we're going to call f of t the amount of C14 after t years. So it is decreasing exponentially. That's how the graph looks like. Initially, we have no idea. The only thing we know that it loses half of its value after 5,730 years. Okay. Another question is, what's the rate? They want R. It means how slow it is decreasing. How slow it is decreasing per year. It means per year, it's decreasing by a certain percent. How much is the percent? All right, so it's verbatim like the previous problem. So we know that after, so initially the only thing, so this is my function. What do I know about it? What I know is at t equal to 0, I basically don't know its value. It's just A. But I know that after 5,730 years, that's another info I have, it's half of A. That's really the information I have. The first one I can't use because they're not giving me anything. That's the piece of information I'm using. So I know that after 5,730 years, the output is 1/2 A. But what is the formula here? I forgot to write the formula. We're assuming exponential. It means f of t is a b to the t. That's really my assumption. And I actually want the b. So I substitute. This will give me a. So it's verbatim like the previous problem. Equal 1/2 A. And the question is, solve for B. And then R. So I divide by A. We got rid of it. So it's exactly like the previous one. It's 1/2. So it means I want to get rid of this power. So basically, But the way we're thinking is as follows. If you have 7 to the power 30 and you raise it to the power 1 over that, it's basically those, you multiply the power, this will give you the b back. So that's how I am trying to get my b back. So it's gonna be, will be 1/2 to the power 1 over that number. So b will be like before, so it is 1/2, which is 0.5 to the power 1 over 5,730. So it's very small, so I'm getting 0.9998. This is 1 plus r, and that's the r that I want. So my r will be b minus 1, and I will keep the number on the calculator because this number are really, and we'll get minus 0.000209. So it's decreasing again at a very slow rate because the half-life is actually huge, 5,730.
Okay, I feel confused. What does your calculator say?
Okay, the calculators say e to the minus 4. What does e to the minus 4 mean? Does anybody know what it means?
No.
It's 10 to the negative 4. Okay, it means like it's this number divided by 10,000. So what they mean
1 over
is,
10,000?
yeah,
Wait.
it's, let me tell you exactly what this means. Okay, so I got minus 0.2096
Right.
times e to the 4. E to the 4, it means 10 to the negative 4. Okay, that's really what it means.
God, that's awful.
Okay,
Why doesn't the calculator just do that? Why does it
I don't
have to do
know.
all that extra
That's how
stuff?
it is. That's what it is. So that's divided by 10 to the minus 4. And then basically you go back to actually whatever in middle school, it means divide by 10 to the 4. And then you ask yourself how many decimals you really need to go. So this is going to give me minus minus 0.000, sorry, I forgot 1 here. Okay, minus 0.00122096. Okay,
Jesus Christ. Okay.
it's a very, very slow, small rate, as I said before. Yeah, the calculator does write always e to the minus 4, which really means 10 to the negative 4, means you're dividing by 10 to the 4, and then you use the idea of decimal and how many decimals you have to use. Right, any other questions before those two, beside those two? So before we start the last two ideas we want to talk about in this course, I will just want to make sure myself. I'm going to pick 2 problems from the stuff I've assigned and make sure all of you got it, and I will appreciate the answers from you. And then we will proceed to the last few ideas. So I'm going to pick, I have no clue, I will pick number 3. And I'm going to pick 2 problems. I will do number D and E. Okay, just to make sure you have, algebraically, you can actually handle those type of problems. So I will start with D. It's very similar to what I did in class. So it's ln of x plus ln of x minus 4 equal to ln of 21. And the question is, solve for x. Okay. And you guys, because you did it, I want you to walk me through this problem so we can finish it quickly. who would like to walk me through those problems, please get started.
Which one is this?
This is number 3 on section 4.2.
Oh. You have to use that first rule
Which
where
is
ln is a times b because you're adding.
ln of a plus b is ln of the product. So we will start with this rule and then go on. So this will help me basically to combine those. So this will give me ln. I'm going to open bracket. X times x minus 4, close my bracket, is the ln of 21.
Right.
And then I say, okay, if those are equal, it means if I take e to the power, the first term is e to the power, the second term.
Right.
And the power of this is the fact that e to the ln of whatever you put here, you get it back. So e to the ln of, this is my box in this case, x times x minus 4, e to the ln of 2, this
1.
okay?
It's 21.
21, thank you. And now the rest should land me into a quadratic equation. I solve the quadratic. And then when I hit quadratic, I wonder, I say, can I factor or I can't? Now, when I see 21, I see 4. Of course, 7 and 3 should jump to our mind. And minus plus, and because I doubt myself, I always double check, x squared plus 3x minus 7x minus 21. So this is equal to 0, giving me 2 values of x. X minus 7 equals 0. It means x is 7. X plus 3 equal to 0. Give me x equal minus 3. And the last step is, as we did last time, which values is acceptable and which values is, yes, the positive. It's not always to know which one. You take the value like x equal minus 3 and you plug it back here and you see, does it make sense? ln of minus 3 doesn't make sense, therefore we stop. So x equal minus 3 not acceptable because you plug it back into the original one. Because if we plug it into the original equation, we get ln of minus 3, which is not defined. So this is get rid of. X equal to 7, let me check it. ln of 7 makes sense. ln of 7 minus 3, it means ln of 3 makes sense. It means x equal to 7 is a value that we can accept. And that's the only one we have. Okay. All right. So there are one type of problem I decided I want you guys to go back again when I have a difference between them. And I insist that you review this one as well. Okay, today we're going to do, as I said, the last 2 ideas in this course, which is the following. Exponential function. The idea is we can write exponential functions. So far we found one way we've actually talked about. Every exponential function could be written in the form a times b to the t. That's how we wrote them. And the idea where b is 1 plus by how much our quantity, by what percent our quantity increase or decrease. So that was what we did. Today, we're going to say that we can rewrite this, not change. we're going to rewrite f in a different format. So we're going to play a game and rewrite this function into the following form: e to the kt, where k is a constant. Now, of course, you're going to tell me, why do you bother to rewrite the function since we understand it this way? Actually, honestly, the main reason is the following. Exponential functions are extremely important because they represent the growth of a lot of quantities. Population usually grow exponentially, money grows exponentially, a lot of chemicals grow exponentially. There are such, the viruses that we went through and we're still going through also grew exponentially at some point. So a lot of functions grow exponentially. So they are extremely important functions. And calculus, that I know that some of you will have to take, works well with E. It's easy to do calculus in this format than to do it in that format. So that's why we have to learn how to write exponential using both approach. So let us see, so the question is, how can I turn something like that into something like this? And I will elaborate by an example, and then we choose the rule, we find the rule. So how to move? So suppose, and you guys have the notes on blackboards, that's why. Suppose I have a function f. And let us say f is like 20. And it represents a growth by, let us say 2%. So that's 0.02 to the power t. So my b here is 1.02. And my goal is to play a game, some kind of a game, and to rewrite this into this format. All right. Here we're going to use, before I rewrite it, the following important property. If I take e to the ln of 1.02, what does equal to? Quickly.
1.02.
1.02. That's the definition of the law. I'm going to make use of this property right there. So this is my function f. It's 20 times 1.02 to the power t. Instead of putting 1.02, because I said I'm going to bring e to the picture, I will write it this way. So this is the power t. Instead of 1.02, I'm going to write this as e to the ln of 1.02. So I'm rewriting, I am not really changing at all. So that's actually is going to be the key idea. Now this is equal to what? Property of exponential is the following. If I have a to the n, and I raise the whole thing to the power n, this is a to the nm. We multiply the power. So basically, if you remember, a squared to the power 3, it means a squared times a squared times a squared is a to the power 6. So we multiply the power. Why I am bringing this into the picture? Because I have e to the ln of 1.02, the whole thing raised to the power t. And algebraically, this is the same thing as e to the power ln of 1.02 times t. That's how I'm going to rewrite it. So in terms of number, because too much ln and e's, let us bring some numbers to the picture. ln of, I'm going to evaluate ln of 1.02. So I evaluate it, and I get 0. E to the following power. ln of 1.02, according to my calculator, give me 0.198. So this will be 0.
I thought it was 1.04.
Mine is giving me
1.02.
ln of 1. Are we all finding ln of 1.0?
Oh, sorry, that's my bad. That's my bad.
Yeah, that's the calculator, so it's not t times t. So let us sum up what we did. We had this function f. It's a typical exponential function, represents a quantity that's growing by 2% per year. I manipulated algebraically and rewrote it to the form 20 times e to the power a certain constant times t. So what my constant k here is actually this number, which is nothing more than the ln of 1.02, which is in the picture nothing more than ln of b. So if a function is given to us this way, then I can rewrite it absolutely in the following format: 20 times e to the power kt, and this k is nothing more than the ln of b. Vice versa. And I, being straightforward with you, the reason is it's easy to work with this function in calculus. Very easy. It's a little bit problematic for that.
There's
Now-
one thing that's confusing.
Yes, please go ahead, Roxanne.
I thought when we put e to the ln or whatever, you get that back. Like I thought it would just be equals 102, right? So we have to work that out. Yeah, that.
Yeah,
Because like when you raise it to the ln, then you get back to the 102, right?
but I don't want that. I want to keep it as k times t. My goal is to write this way.
Right.
That's my goal. So I don't want to backtrack. I'm trying to move forward to write it as e to the kt. Okay, and my k is going to be that number. So I'm not, you're right, but that's not my goal now. My goal is to take this function and write it as a certain value, 20 times e to the kt. That's really what my goal in this case. And my k is the ln of 1.02. So far we have the following. So if a function has the form a times b to the power t, I can rewrite it as a e to the kt. Means I can rewrite it. I mean, I don't really change it. I'm going to rewrite it. And what is the k will be? So this constant k is going to be what? This constant k is going to be the ln of b. So that's how I go from here to here. K will be given a name, and we will call it continuous rate. K will be called the continuous rate. So K will be called the continuous rate. That's the name it will be given to it. Now, let us say I'm starting with, so suppose somebody tells me you have an exponential function. And they tell me, okay, f of t, so they did not give it to me in the form a times b to the t. They told me this function has the form 20, so I'm gonna go backward now. Understand that. Suppose somebody tell me f of t is 20 times e to the power 0.5t. We haven't seen an exponential given this way so far. So the question is, how can I rewrite it in a format that I can recognize? So we're doing two ways. We're going from ab to the t to ae to the kt, and now I'm going to take you backwards. It means if somebody tells me this is your function, how can I recognize it as a times b to the t? So let's see which game I'm going to play. I'm going to take e to the 0.5t and rewrite it e to the 0.5, the whole thing to the power t. Okay? Am I correct algebraically? Which property I am using? I'm using the property an to the m is a to the nm. It means 0.5 times t give me 0.5t. At this stage, I am actually honestly done. why I am done. This will be my B that I will be looking for. So if I compute e to the 0.5, I will get the following. So I will do that on the side. E to the 0.5, sorry. E to the 0.5, I'm getting 1.648. So this will be 1.648. It means e to the 0.5 is 1.648, and that would be my B. So if somebody wrote the exponential function for us in this format, the question would be for us, okay, what does it mean for us? How can I rewrite it as a to the b to the t? So we play this game, we keep it 20, e to the 0.5t, I rewrote it this way. Now, this would be my b, 1.648. Now, the benefit of that is now I know what's the rate. So if I have a function, somebody write it like this, for me, I don't understand what's the rate. Now I understand that this is a quantity that's growing at the rate of 6.48%. That's really the rate at which it's growing. This really doesn't tell me very clearly the rate, but this will tell me the rate. This is easy to use in calculus. This is harder to use. That's why we have to know both of them. Okay, so let me summarize the whole thing, because e to the kt is going to become an extremely important function for you. So, summary. Okay. Exponential function, we can write them in two formats. A, b to the t. That's the standard format that we like. Hopefully we understand. But also, we can write them e to the kt. So two different ways of representing the exponential function. T is my input. A, B, K are constant. A, B, K are constant. B is the regular B, is the growth factor. K is given a name, and it's called the continuous growth rate. It should remind us the continuous compounding. Continuous growth. But what's the relationship between them? The relationship between them is the following. B is e to the k. K is the natural log of b. So in other words, if you know k, you can figure out b. If you know b, you can figure out your k. And before we practice those, which is not going to be very hard, very important note. Quite important. Now, if you have a function of the form a times b to the t, how can you tell whether it's increasing or decreasing? Question addressed to you. So if you have a b to the t, how can you tell whether increasing or decreasing?
If it's more than 0, it's increasing, and if it's less,
No.
1.
It's
More
more
than
than
One.
one.
Yeah,
One.
1.
So b greater than 1, increase, growth. B is always positive. B is always positive. Decay. But very good. What about K? If somebody gave me the form of the exponential this way, a to the kt, when do I know whether it's increase or decrease? And let me help you with it. We know that B is e to the k. So which value of k will make B bigger than 1? Let me take you back to the graph of the exponential. Suppose this is, let me call this x, and e to the x. E is a number bigger than 1. It means this exponential function is actually going to increase, and this value of 1. So 1 is e to a power bigger than 1. If x is positive, e to the x is bigger than 1. E to the power a half, e to the power 2, 3 bigger than 1. However, when the input is negative, this is e. E to the x is going to be less than. So that's how the exponential behaves. Why I am bringing this back here? If k is positive, the b, which is e, is going to be bigger than 1. So if k is positive, we have an increase because the b will be bigger than 1. If k is negative, so that's very different. The b is e to the k, and when we start raising the e, so this is my e, this is my e, no, this is a 10, sorry. This is my e. If I start raising it to negative numbers, let us say -1, I start getting numbers less than 1. So this is less than 1. It means I will have a decay. So if my exponential is given ab to the t, we have growth, b bigger than 1, k, b less than 1. If my exponential is given a e to the kt, growth, k positive, decay, k negative. Very important to know the behavior of a to the kt. So before we start moving back and forth between those way of writing an exponential, so I'm going to write some exponential in the form b to the t or e to the kt, and my question is only, is it increasing or decreasing before we move on? So suppose, by now of course I'm going to answer quickly, suppose f of t is 200 e to the 0.2t. What is the case that I am talking about in this scenario? Can you
0.2.
0.2 has nothing to do with t. That's my k. 0.2. This is positive. It means that we have growth. Okay, I'm not finding b on purpose. I want you to, when you see it, to realize. It means when I'm graphing this function, how it's going to look like. At 0, if t is 0, I will have e to the 0, so it starts at 200. And because k positive, that's exponential increasing. Okay. Now, of course, if I take 200 e to the minus 0.40, my k is this number right here. That's my k. That's negative. It means I have a decay. It means if I take my calculator and I sketch this function, so suppose I take my, I have to change a little bit here. Why don't you guys graph it a little bit? And I have to change a little bit my mode. Okay. So if I take my y and I sketch the function 200 times e to the power minus 0.4t. Okay, and I graph it, but the initial value is 200. So we have to make sure, watch what I'm doing. I know that initially it's 200, so it means I want my y range to be, if my y range maximum value is 2, it's getting me nowhere. So I want the y range to be -2 and t to be something like 400. And after that, I'm going to graph. It's definitely a decreasing function. That's the effect of k. So this will be If t is 0, I am at 200. And this will be a decreasing function. It's always positive, but it will be decreasing. So whenever I see a function of the form 200 e to the kt, the sign of k tells me whether it's increasing or decreasing. Now we will take some problems where we will move back and forth between both ways of writing the function. So so example, and my question is the following, which is of course on your notes. So I read the question and then we do the problems together. So the question is simple. The question is, for each of the functions below, do the following. If the function is of the form ab to the t converted to ae to the kt and vice versa. If it's in that form, convert it to that. And decide if the function is increasing or decreasing, because I want you to realize that the sign of k affects this issue. So we will start with some problem. So the first problem I have it for you is f of t equals 1000 times 0.9 to the t. So, and the question is, I want to rewrite it in the form a e to the kt. That's what I want to rewrite it like. So how can we do that based on what we did? So here we know the b, which is okay, that is a decay. We know that that is a decay. And this is representing quantity decreasing by 10% every unit of time. So to write it, e to the kt, I have to find my k. My k is the natural log of 0.9. And we will compute the natural log. Are we going to get a positive number or a negative number?
Negative.
Immediately negative, because the b is less than 1. So I'll go back here and I compute my ln. No, sorry. I compute ln of 0.9 and I will get minus 0.01536, so that that's kind of rounded up to 4. So what does this mean? It means my function could be written as 1000 times e, so the initial value does not change, e to the power minus 0.1054t. K, this is called the continuous growth rate, because I want you to know the K we call the continuous growth rate. So what does it mean to you? So I pick up my calculator, for example. I sketch this function. I sketch this function. What do you think is going to happen?
The same.
Increasing.
Exactly the same. Nothing changed. If I plug in 1 for t here, 1 for t here, I get the same answers. 2 for t here, 2 for t here, I get the same answers. What's happening is just a different way of writing the same thing, because as I said, those will be easier functions to work with. Okay. Now I will do 2 more, where I'm going to move you to the other, from E8 e to kt to the other format. So I will pick one problem. So this is equal, again, I picked like 1000, it's nothing, minus 0.02t. And the question is, write it a times b to the t. So first thing is, what is my k here? My continuous rate.
Negative 0.02.
Negative 0.02. That's my k. Okay. And I have to write it in the form a. A is this carry for both values, b to the t. That's really how I will need to write. So now I remember what's the relationship. So I know the k, what's the b? The b is, if you ever forget, this is easy. The b is actually this piece right here. That's the b. That's the b. That's exactly what the b is. So this is e to the power minus 0.02. I should get a negative number because the exponential function, that's the exponential. We have a negative number, the exponential takes a value less than 1. So we will get that. So this is e to the power minus 0.02. And unless I'm goofing, I'm getting 0.98. So with this in mind, my function f of t will be equal 1000 times 0.98 to the power t. Okay. So by rewriting it this way, suppose I ask you the following simple question. This is a decay. So by which percent is the function f of t decreasing every year? Can you answer this question easily? By which percent it is decreasing? Now I rounded a lot, so I should have, sorry, I'm going to round a little bit less than that because those numbers are so close. 0, 1. So by how much it is decreasing, I have really a good understanding here. I just take a 1 away from that, and it's decreasing. So if I want the rate, it's always b minus 1. So if I take this number, take away 1 from it, I will get minus 0.0198. It means this is decreasing at the rate of 1.98%. So that's my rate. It's negative because it's decreased, and decreasing at the rate of minus 1.98%. So it really tells me by how much it's decreasing when I know the b, so we can understand it better. But this will be easier to work with eventually. Now, one way to understand this is that 2% continuously is like 1.98% per unit of time. That's another way to understand it. So decreasing 1.98% per year is like a continuous decrease of 2%. Okay. All right. Now, on your notes, we have 2 other problems. I will pick one of them maybe, and we work it together, and then we finalize with the last piece. So, okay. We will do this problem together. The population in Washington state in millions is given by this function. So as I said, a lot of times population is given in this format, where t is number of years after 1995. So the first question is find the population in 1995. So what's t in this case?
I don't know.
Think for 1 second, not more than that.
Would it be the initial
0?
t?
Right, t equal to 0. That's the initial.
Yeah.
Yeah, because t is the number of years after 1995. I'm asking, okay, what is the population? T equal to 0. And we know what it is. It's the initial. It's 5.4 times e to the power 0, which is 1. It means 5.4 million. Is in 1995, the population in Washington state was 5.4 million. Now, what's the population continuous growth rate? This is the K. So this is the K. It means the K, that's the continuous. 30. Okay. Now, when will the population triple in size? Is this an easy question or a hard question? Easy or hard?
What?
Is this an easy question or a hard question? Quickly.
It's like double time, but it's triple time.
It's triple time. So how can we solve it?
Set it equal to 3a.
Set equal to 3a. So we're going to set this times e, because it's in e in here, And since it's in E, I have to work with the E. So I put my parenthesis, I was wrong. It's in E to the power 0.013 T equal to 3 times 5.4. Okay? So we have to solve for T. So we're gonna set this and solve for T. So you can multiply those out and divide by 5.4, or we divide by 5.4. And I get E to the 0.013 T equal to 3. Now I need T. My T is an exponent. Now I have to use the natural log because the unknown is an exponent. So now I said the natural log of the first equal to the natural log of the second term. So that's E to the 0.013 T is equal to that. It's already easier than dealing with the other format because ln of E to anything, this will give me 0.013 T. If you want times the ln of E, but the ln of E is equal to 1, equal ln of 3. Okay? It means T equal, so ln of E is 1, so I don't have to keep carrying it. So this will be 0.013 T equal ln of 3. And this will give me my T equal natural log of 3 over 0.013. So even simple equations like that, it's easier to solve them with the ln actually, because the ln and the E will cancel out. So this will give me the ln is, sorry, the T is ln of 3 divided by 0.013, and I'm getting almost 84 years, 0.50. So if this model for the population of Washington State remains, it will take 84 years for the population to grow to a little bit over 15 million. I don't think it works. Now D. My question D that I erased here was, by what percent does the population grow every year? What do you think I need to do? So my D is, by what percent?
Try to find the growth rate.
I have to find the growth rate. By what percent does the population grow every year? Means assuming the population in Washington State kept following this model, kept growing along this, kept growing like this formula. And the question is, by what percent is it growing every year? So what do I need to be able to answer this question? Back to you.
Calculate E to the 0.13.
Yes,
And
I need to find, yeah, I need to find R, the rate. To find R, I need the growth factor. Okay, that's what gives me exactly by how much is growing every year. So I take another piece of paper and I go after the growth factor. So now we need the growth factor. So by what percent here, we need to find the B. Okay. So to find the B is, so let's see, I'll show you the B over and over because I want you to see the B. So I will write my function again here in front of me. It's 5.4 million, that's what it started. E to the 0.013 T. That's the original. To find B, as I said before, this is the B. That's really what my B is. So my B is E to the 0.013. And now I compute that, and then I can basically figure out the rate. So, what is my E? My E is here, 0.013. I'm getting 1.01308. And this is 1 plus R. So my rate is this exact same value. I'm going to take 1 away, and it's 0.01308. So the actual rate is that the population is growing at the rate of 1.308%. So that's the population growth in the state of Washington, granting that this model is kept. Okay, that's how we analyze those ideas.
Excuse me.
I'm listening.
How did you find the constant rate again?
The K.
Yes.
Okay, I will give you several examples, and it's what comes next to T. Okay, so suppose I have a simple problem: 2 times e to the 4t. Okay.
Mm-hmm.
The K is what comes next. This is the K. It's the 4.
No, I
Okay,
meant,
go ahead.
no, I meant for the model that you used for the previous problem.
The K is the ln of B. So if you have the B, are you asking about the, okay, I'll try to follow. So suppose in my model f of t is this problem you're talking about.
Yes.
Okay, so it was 0, what did I give you? 0, 1, 13 t.
Yeah, that's what I meant. How did you get
It's the
0.0113?
coefficient of t. It's what t is multiplied by. The k is what t multiplied by. So when I write 0.013 t, what really I mean by that? I mean 0.013 multiplied by t. I hope I'm answering the question. I'm trying.
I think he's wanting to know how you convert it into the other form so that it's
You have to
got a
multiply
growth
E
factor.
by K to get B. E times K equals B. T don't even look at T. E times K equals B.
e to the power k, Roxanne.
Power K, whatever.
Yeah, e to the power k. So that's really my k. It's the what we call the coefficient. Is the number that t is multiplied by. So here, my k is 0.013.
And then what's B? Show him what B is.
B is e to the k. Means e to the power 0.013.
You put that in the calculator and that gives you what B
Yeah.
is.
Yeah, we plug in into calculator. I don't know if I'm answering the question. I'm trying. So suppose I put f of t equal to e to the minus 0. Minus 0. Okay, actually minus 40. What's the k? The person who asked me the question, what do you think the k is?
-4.
-4. Did you understand what it is? It means this is -4 times t. That's really how we read it. So k is the coefficient of t. That's how we pick up the k. It has nothing to do with t. It's a constant number.
What are you doing?
All
And
right?
then what about, and then show him how to get B, how to
B
convert that.
is
No.
e.
No, I already know how to get B.
Yeah, it's the k that's giving him
Oh
problem.
man,
Yeah.
why?
Okay? I can give you tons of problem along those lines. I mean, any problem, you know, it's 2 e to the power a, I don't know, 100t. K is what t is multiplied by. The k is 100. All right, I'm answering your question now.
Yes.
Okay, all right. Now so this is the two ways of writing exponential, and as I said, important. I'm not giving you a headache. Important because that's how most of the exponential function will be represented using the e, for the simple reason calculus is easier with it. That's really why they use e instead of b to the t, because people do a lot of calculus with those kind of functions. They are very important functions to work with. All right, then I think we will talk about is, I will go back to the ln function, and how does it, what's the graph of it? How does it look like? Please ask question as I move on. Okay. E to the x, we mentioned how it looks like. So the graph of e to the x, so if f of x equal e to the x, it means f is a function. In input x, it output e to the x. E to the x, the graph is an exponential. Initially, if x is 0, it's equal to 1, and it is increasing. Now, we will talk about the function. We use the ln so far to solve problem where the power is unknown. So now we're going to talk about the function fx equal ln of x. It means, what is a function? It means we will talk about the rule that assign to every x the number ln of x. This is the rule we are talking about. The first question is, whenever you have a function, is ask ourselves about the domain of this function. The domain. The domain, it means which input will spit out an output for me. And here we know which input will actually spit out an output. Only positive input are allowed. So the domain are all values of x such that x is strictly positive. Okay. Now 2. I would like to sketch the graph of ln. And because you should know the graph. How does this function looks like? Now, how we sketch the graph of a function? I will take a bunch of input values, so values of x, and I will take values of the ln, and I will plot point. Now, I know that I cannot take any negative value because ln of a negative value is not defined. So I have only to take positive values. So I will take 1 and 2, 3, 4. No, sorry, my apologies. I will take 1, and instead of taking 1, 2, I'm going to take very specific value, e. Remember, e is 2.71. And for a reason, I'm doing this definitely for a reason. E squared, e cubed. So I'm taking very odd values, but they are easy to work with. And here I will take small values less than 1. So I will take 1 over e, it means 1 over 2.7, almost a half, or e to the negative 1. And I will take something less, e to the negative 2. And I will stop right there. And I would like to sketch the graph using those odd values. First at 1. What is my output at 1? ln of 1.
0, right?
0. I want to choose very important value of the natural log. ln of 1 is 0. So at 1, I am right here. Now at e is somewhere here. What is the output value at e?
2.71.
Yes,
No?
or no. What's the ln of e? Again, if you ever forget, you go back to the definition. What is ln of e? the power of E, that gives you E. That's the definition. Which power of E gives you E? Is 1. So ln of E is equal to 1. It means if this is E, the output is 1. So that's my second point. All right. So I'm going to a little bit scale down my graph so you guys don't have to do anything, but I'm going to take a little bit smaller values. So I'm going to let my 1 to be here, and I want to let my E to be here to have a better graph. So this is the point E for X, the output is 1. All right, so now I have 2 points. What about E squared? E squared is a larger number. It's like 7 point something. So E squared will have to be somewhere in here. What's the output?
2.
2. Okay, and that's why I picked those values, because the output is easy. If I put like 1 or 2 and 3, the output is hard. So I put those weird values. So this is like 7 point something, because I want a nice output. So this is 2. So E squared will give me 2. So this will give me 2. So if an input of E will give me a 2. And then the picture will continue. If I take E to the power 3, it gives me 3, and so on and so forth. So I'm going to connect the dot. This will be actually concave down as a graph. So far. That's part of the graph. Now the hard part is here. How does it look like here? And what type of values does it take? Positive or negative values?
Negative.
Negative, and that's important. So if I take 1 over E, now it means 1 over E is somewhere in here. 1 over E, that's ln of 1 over E. 1 over E is ln of E to the negative 1.
Negative 1.
Negative 1. So when I want 1 over E, it's going to take the value negative 1. If I take a smaller number, of course you see the picture. Negative 2. So what's going to happen? How is the graph going to look like now? Can you think of a value where the ln takes the output minus 3?
1 over E to the
To the
third
power 3. Will it ever take the value minus 100?
Yeah.
Yeah. So how the graph look like? It will never stop going down. It will keep going down, getting more and more and more negative. So as the input as X gets smaller or become close to 0, gets smaller, my output is getting more and more and more negative. It never stops. It never hits the y-axis because there is no output for X equal to 0, but it keeps getting more and more and more negative. So sometimes we say that when the input X become close, very close to 0, get very close to 0, the output, it means the value of the ln of X, what happened to them?
They become negative.
Negative, yeah, more. Become more and more negative. Does this make sense?
Mm-hmm.
As we get close to 0, they become more and more and more negative. They become more and more negative. Okay. Now, sometimes in math, we express this idea. The value of ln become more and more negative. We say that the values of ln of X goes to, what do you think I'm going to write?
I have no idea.
Anybody has an idea? Do they ever stop becoming negative?
No.
No,
Oh,
it's continuous, right?
Right, continuous. So in math, we express this idea. We express this idea by saying that they will go to minus
Infinity.
infinity
Oh, okay.
or minus infinity. Okay, that's an idea. So we express this by saying that as x become close to 0, the value of ln of x will go to minus infinity. They express the idea that they never stop from going down. And the same thing, we say that when x gets larger, also the value of ln gets larger. So we say it's when x goes to plus infinity, means when x, the input value become very large, the output also become very large. The output also go to plus infinity. So I can ask you the following question. Will the value of ln ever stop growing, or they keep growing? What do you
No, they
think?
keep growing. Whatever
if I-
number you put in there.
If I put 100, is there a value of x that will give me 100?
Yeah, e to the 100.
E to the 100. It's a huge value. E to the 100 is an absolutely huge value. I don't know if your calculator even pick it up because how big it is. So that's.
It's gonna do that thing where it makes us
All right.
divide by 10 to the
Math,
whatever.
it's positive. So it's 2 to the power 43 times 10 to the power 43. How big is this number? Do you know what 10 to the power 43 means?
It doesn't fit on my calculator.
How many zeros we have? 43 zeros. So it's a huge number. It's a number beyond our whatever human understanding. It's a huge, huge number. E takes very large value. When you start taking e to powers, the numbers become very, very large. Even if you take e to the power 10, you get a very large number. Let's try it. E to the 10 is 22,026. So those numbers grow very, very, very fast. The exponential grow very fast, but the natural log doesn't grow very fast. Okay, so that's the graph of ln of x. Okay, at this note, I will definitely finish the today's, and you guys will have homework. Your final exam is on a Wednesday, of course, not this Wednesday, and everything will be put on Blackboard very clearly. So your final exam is on Wednesday. I think it will be May 6th. And the final exam will be from 5 to 7 in the evening. It will be a comprehensive. You will have a review by Wednesday. The review will be basically a review 1 and review 2 for both exams put together with some problem removed, so you don't have to do the whole thing. And I will add some extra material for what we did at the end. For next time, you will have a quiz as usual. And I would like you to bring with you, you can ask any question you want. I would like you to bring with you the exam 1 and exam 2. So I can review some of the concept that I remember that you had to struggle with. Okay, so bring with you exam 1, exam 2. We're gonna review some of the concept you had struggled with, and I'll answer any questions you guys have from the material. And anything else? No, do you guys have any questions?
No.
Nope.
Okay, the last thing I wanted to do, you guys have the evaluation, as you know. I really would like you to fill out those evaluations. Very few of you did. Please fill them out, or I will give you a very, very hard fine. So you may cut. Is that very clear?
Yes, ma'am.
Okay.
No evaluation, hard fine. I don't think you want that. So
No.
I will decide by Wednesday whether it's going to be hard or not. Please do fill them out.
All right, have a good night.
Okay, so good night, guys.
Good night.